Hello! First of all, I want to thank the organizers for this nice virtual meeting on homological algebra. My name is Ivonne Dorado, I work at Universidad Nacional de Colombia in Bogotá, and with this video I want to show you how I've been using GeoGebra as a visual tool to study representations of p-equiposets through its quadratic forms. As they are polynomial, then I graphic some polynomial equations to obtain information about the categories of representations I'm interested in, and it allowed me to present things in a more visual way. For example, this picture here is the slender-rated quiver of a 10 p-equiposet. These posets are finite posets in which to each pair of comparable points we assign a number between 1 and p satisfying this condition. That means if we assign, for example, L here and M here, those are arbitrary numbers between 1 and p, then this n we assign to this relation is greater or equal than this number. Then the order relation splits in p relations and we distinguish two. If we assign 1 to a pair, we say they are in weak relation, and if we assign p, we say the relation is strong. For the points, we have only two possibilities. A point can be in weak relation or in strong relation with itself. Then we have two kinds of points and p kinds of order relations. Then in the Hasse diagram, we mark some points with a p, which mean they are weak, and the points we leave it with no mark are strong points. Now we choose a field extension of degree p and the algebra of F endomorphisms of G and some subspaces of this algebra. Now in the Hasse diagram, if we have weak points, we assign G to these points. These X, Y, and Z are just to identify the points. For the strong points, we assign F, and in each relation, we assign a subspace with the dimension corresponding to the number we assign to the relation. Now, here we have elements of the algebra, and also here, then we can multiply those elements and we will have an element from here. That's one of the reasons for this condition here that it seems so technical at the beginning. Here, notice that we have here some kind of realization of a species. A representation consists in assigning a G vector space to the points we assign the field G, and F vector spaces to the points we assign the field F. At the edges, we assign monomorphisms between the corresponding vector spaces, respecting the structure we define in this way. To study these representations, we add a maximal and minimal point to the poset, and we construct a one-Gorenstein basic algebra which has one simple projective module, one simple injective, and a module which is projective and injective associated to the minimal point. We prove that the categories of representations of a p-equiposet are equivalent to the so-called projective lambda modules, and also to this subcategory of morphisms between projective lambda modules. All these constructions and equivalents are in these papers. For anyone who's interested, you can find the links in this video's description. And in this subcategory of C2Proj, we have the Euler bilinear form. Of course, we have a quadratic form when y is equal to x, and with this form we count, of course, the dimension of the home space minus the x. The form of the objects allows us to assign to each one a coordinate vectors whose entries are the number of times each lambda projective module appear in the decomposition of the domain. So the entries are natural numbers, and we have one coordinate for each point in the poset and this additional number. So we have vectors with cardinal of p plus 1 entries. We prove we can evaluate the Euler quadratic form of each object by evaluating its corresponding coordinate vector in this quadratic form, which depends only the numbers we have assigned to each relation. So it depends only on the form of the poset, and it can give us, of course, the dimension of the endomorphism space minus the x. This x is trivial if the object is in the post-projective or projective component in the Auslander rectangle. So then the quadratic form will be equal to 1 when the endomorphism ring is isomorphic to the field F. And if the endomorphism ring is isomorphic to the field G, then we will have that the quadratic form is equal to P. And in both cases, we will have one representation up to isomorphisms with the same coordinate vectors. If the quadratic form is equal to 0, then we know that the coordinate vector corresponds to a parametric family of infinitely many representation non-isomorphics. Then the poset is of tame representation type. If the quadratic form is less than 0, we know that the poset is wild. So we can obtain information about our representation category using the solutions of these equations and this inequation. We will see some examples in which we are able to graph these quadratic forms as they are polynomials in cardinal of p plus 1 variables. Then if the poset has at most 2 points, we can graph these equations in 3 dimensions. We will consider the case of 3 equipped posets. In this case we have these 2 kinds of points, and we will consider poset with 2 points of this kind. These 4 posets. We're beginning with this one, which consists in 2 points in relation 1. L00 is equal to 1 because 0 is the minimal point we add and we consider it as a strong point. Then LAA and LBB are 3 because we marked the points with these 3, and LAB is also 3. Now this is the quadratic form. X corresponds to the coordinate 0, Y to the coordinate of the point A, and Z corresponds to the point B. Now we will search for vectors that satisfies these conditions. Recall that the vectors are coordinate vectors, so its entries are natural numbers. So let us first look if the poset is a wild poset, so if there are vectors in which the quadratic form is less than 0. First we set a list of points with natural coordinates, this list here, and we search if some of these points we construct here with this instruction in GeoGebra, and with this other instruction we evaluate the quadratic form in each point, and we keep the point if the quadratic form is less than 0. Then we are constructing another list here which is empty, but let me hide the first list. Yes, now this list is empty, so the poset is not wild. To determine if the poset is tame representation type, we graph the quadratic form, which is this polynomial equation, equal to 0. And we obtain a line, this line here. Now, in this line, we can consider just the points with natural entries, and we have the list here. These points in gray, they are coordinates of some parametric families of representation with infinitely many indecomposable modules non-isomorphic. So with this information we conclude this poset is tame and is of course a one parameter poset because a line, the points on a line are scalar multiples of this first point. Now let me consider the quadratic form equal to 1, this polynomial equation. The graphic is this tube, is not a perfect cylinder because it is somehow elliptic, this point. And on this tube we can consider the points with natural entries, or those in purple, in violet. So these points are coordinate vectors of a representation, and to each vector corresponds just one representation up to isomorphism, as well as in the natural vectors with natural entries on this tube in yellow, which is the quadratic form equal 3. The representations corresponding to these points are representations in the post-projective and projective component of the Auslander-Rayton quiver of the representation of this poset, which are so-called projective modules over this matrix algebra, which has these 3 projective modules, and this distribution in the Auslander-Rayton quiver. These are the projective modules and the morphisms between them. So we compute the coordinates of the modules, and we find these morphisms in our tubes. On this side of the tube we find the injective representations, well, the injective coordinates of our representations and morphisms between them. This algebra is hereditary, so we can compute the Cartan matrix, and with this matrix, the Coxeter matrix, to obtain the Auslander-Rayton translation of each coordinate vector. So in the purple tube, the Auslander-Rayton translation looks like this. This representation goes to this one, and the vector corresponding to the representation up here goes to the representation below, and comes back and is the same here and all around the purple tube. The Auslander-Rayton translation on the yellow tube looks like this. So we have these modules go up and down and then up, and the modules in the middle just go in a line. And it's the same in this component will be the projective component, and the translation looks the same. So the Auslander-Rayton quiver looks like this. We can divide these two tubes, and we have one side the post-projective and projective components respectively. Following our computations, we have irreducible morphisms between the representations in these cycles here to the representations on the parametric families. Let me hide something to show you this one. And the Auslander-Rayton quiver looks like this on the tubes determined by the quadratic forms equal to 1 and equal to 3. Now let me go to the second example. Is this poset 2 weak points in relation to. This example is different from the previous one only because of here we have 1 and here we have 2. So the quadratic form will be only different in this LAB. This is the quadratic form, and let me see first if this quadratic form corresponds to a wild poset. We have again our list of points, and we choose from this point the points which evaluated in the quadratic form are less than 0, and we can see the list is empty. So this poset is not wild. Now let me draw the quadratic form equal to 0. Is this line, and notice its intersection with the first octant is just the null point. So this points on the line cannot be coordinate vectors of any representation, and we conclude this poset is not tame. So it could be only finite representation type. So let me show you the graphic of the quadratic form equal to 1. The points with natural entries on this tube are these points, and if we draw the quadratic form equal 3, is this tube in yellow, and the points with natural coordinates are this one in pink. So here we have the coordinate vectors of representation of this poset are finite, so this poset is finite representation type. Category of representation is equivalent to the so-called projective module subcategory of this algebra. This is a GGB module of dimension 2, and its Aullander-Roy quiver was described in this paper in another context, and it looks like this in our on our tubes. Notice that we have morphisms from the representation on one tube to the other one. Now let me show you the third example. Is this poset 2 weak points in relation 3. This is the quadratic form, and let me see first if it can be a wild poset. We choose again the points which evaluated in the quadratic form are less than 0, and notice that this list is empty, but this is the quadratic form equal to -1. This is an hyperboloid, but it has no intersection with the first octant, so there are no points with natural coordinates in this hyperboloid. This is the quadratic form equal to -3, equal to -0.01. So we have these surfaces, but they have no intersection with the first octant. When the quadratic form is equal to 0, we have this cone that doesn't have any point with natural coordinates, so this poset isn't tame. This is the quadratic form equal to 1, this hyperboloid, and we choose the points with natural coordinates on its surface, and here we can see all of them, and this is the quadratic form equal to 3 with the natural coordinates on it. So this poset is finite representation type. We have only finitely many coordinate vectors of representations, but notice that they all have a null entry. So we say this poset is not sincere, and we can prove every representation of this poset is equivalent to a direct sum of two representations of the poset with just one weak point, this poset. Now let me show you the last example, which consists in 2 points uncomparable. This is the corresponding quadratic form for this poset, and when we choose the points that evaluated in this quadratic form are less than 0, we found all these points. So we are here in a wild problem. Here we have the quadratic form equal to -1. It seems we have no points on this hyperboloid. Here we have the quadratic form equal to -2. This is another hyperboloid, and we have some points on its surface. I will choose only the points on this surface. We have those points here. We know that the classification of these representations includes this problem of this Kronecker problem with 3 arrows. But we can say some things about this representation category. Here we have the quadratic form equal to 1 and some points on this surface, and here we have quadratic form equal 3 and some points. We know that these points are in the component of the Outlander-Rayet enquiver of the simple projective module of this matrix algebra. And this algebra is also hereditary, so we can maybe construct also Cartan and Coxeter matrix to obtain more information. But if we choose the quadratic form equal to 0, we have this cone. So when we want to study the moduli space of this representation category, maybe we will have to consider the geometry on this cone here. Now, in this way, we have some this visual help to study our categories of representations. Before I say goodbye, let me say thank you to some students of the mathematics program at Universidad Nacional de Colombia, and thank you all for watching this video. Take care.